Okay, so let's talk about the homework from chapter 3. The first one is 3.1.3. First, the problem asks us to calculate the data from the chart given in the problem to fit the model y is equal to a times x to the power of b. So first, I put our data into the numpy array x and numpy array y, and then we take the login of both data to produce log x and log y. Then we plot it in the graph. We can see the relationship between log x and log y here. And I made a fitting line here. So we can get the slope of the our fitting line is equal to 3.09, and the intercept is negative 5.74. Since the intercept is the log a from the problem, so we can get the a is equal to 0.0032 and the b is equal to 3.0919. So, I think this is a typo here. So y should equal to 0.0032 times x to the power of 3.0919. It shouldn't be this number. I must type it wrong here, but yeah, the correct number should be this one. Okay, let's talk about the second problem from chapter 3.2. It's the number 5, question number 5. Let me pull the problem. Okay, so it's supposed the variable x1 can assume any real value. So it shows the following substitutions using non-negative variable x2 and x3 to permit x1 so that x1 is unconstrained. So x1 is equal to x2 minus x3. So in this case, if x2 is larger than x3 larger than 0, it will lead to x1 larger than 0. So if x3 is larger than x2 instead, the x1 will be negative. So when the x3 is equal to x2, this will lead to x1 is equal to 0. So for this, all of these three cases can produce the can represent the x1, and the x1 is unconstrained. Let's move to the 3.3.5. Let me pull up the problem here. Okay, so it asks us to fit the quadratic in the problem number 3, which give the two sets of data here. First, I also produce a two numpy array here to put all the data in, and we need to fit into this equation here. So we can use the equation from our book to produce a partial derivative of all three unknown variables, C1, C2, and C3. So we can get this equation here. After we rearrange the variables here in the three equations, we can get the final equations that we can use to calculate. So here, so I calculate the x and the x square and the x to the power of 3, x to the power of 4, and the y and xy and x times y. Here I calculate all the summation of from this chart. No, from these two lists, I can calculate of those numbers to in order to for the calculation of C1, C2, and C3 in these three equations. So we can plug in those numbers here. Here I also use Python to solve the three unknown variables. So we can know that C1 is equal to 3.786, C2 is equal to 0.0385, and C3 is basically 0. So the models would become y is equal to 3.786 x squared plus 0.0385 times x. So the second part of the problem asks us to do the same calculation, basically assume the C2 is equal to 0. So y is, in this case, y is equal to C1 x squared plus C3. So the two equation would become this, since we don't need to do partial derivatives on C1 and C3. We can still use the values from above to calculate the two unknown variables. So we can get our variables here. So the equation would become 3.847 x squared plus 0.0047. So it also asks us to repeat the process for the C1 equals to 0 and C3 equals to 0. So we only have C2 in this case. So y should equal to C2x. So in this case, C2 would become the sum of xy over sum of x squared. So we plug in those numbers from above. We can know that y is equal to 1.587x. So for the cubic, the equation will become this one, the a times x cubic plus b times x squared plus dx plus d. So it basically follow the same pattern as given in the book. So we can produce the four equations to solve four variables, unknown variables. So we can following this pattern, we can know that for any polynomial function, we could develop the equation to follow the same pattern here. Basically just same pattern. So for the last question, 3.4.3, import the problem. It asks us to find a model using the least square criterion, either on the data or on transform data from the problem 4b. So I put this is a long set of data. So I also put them in the two numpy arrays, and the way and oh, what's going on over here? Oh, the lattice there must be something wrong with the lattice. I don't know. Okay, let's let me see the problem from 4b in section 3.1. So it gives us equation of p is equal to a times ln v. So it asked us to fit in this equation. So we first calculate ln v. The data is here, and since we know that p is equal to a times ln v, so a would become the fraction of sum of p ln v over sum of ln v square. So I don't know what's going on with the lattice, but it become this way. But let's move on. I use a function to calculate the summation of two values, the p times ln v and ln v square, we can get the value here. Since we can calculate, then we can calculate a. A is equal to 245928. That's a long number, so we know that. Since we know that the deviation is let's say since we know the deviation is equals to the p is minus the number we calculated, so we can calculate all the deviation here. We can easily know the maximum absolute deviation is right here. This number is pretty large here. From all of this data, and we calculate the summation of the square of deviation using this for loops. We can get the number is this one, the huge number. Then we can calculate the capital letter of D here by calculate the square root of these numbers over how many numbers are here, the 15. So the D would equals to 380684. The bound of C max would be between this number and the maximum absolute deviation. Okay, so these are the 4 problems from the chapter 3. Let me stop.